All right, I was just talking about this. Let's make sure that I continue it. So the hanging wall, right? If the hanging wall rises compared to the footwall, that's called a reverse fault. A normal fault is just the opposite, all right? So a normal fault is when the hanging wall falls uh, compared to compared to the uh, compared to the footwall, right? So that's called a normal fault, all right? So that's very important. That this is just showing after weathering. Sometimes it's hard to see that. Uh, all right, so yeah, so with a normal fault, you're basically, if you kind of think about it, you're getting a little bit more land. With the reverse fault, you're losing some land, a little bit of land. All right, so and then there's what's called if the two faults don't change heights, there's no vertical displacement. All right, the height doesn't change at all, but you only have horizontal movement. That's called a strike-slip fault. All right, so probably the most famous one is, of course, the San Andreas fault. So that's, we further classify the San Andreas fault as a strike-slip fault. All right, so um, all right. Remember, it's transform fault. It's continent, um, and it is so um, because there's no vertical displacement. On average, there's no vertical displacement with the San Andreas fault. It's called a strike-slip fault. All right. So, which type of fault is created by the state of Nevada? Okay, so now you really have to look into that. So what's going on with this in the state of Nevada is the the hanging wall is dropping below the footwall, right? And so if you remember, when the hanging wall goes below, that's a normal fault, right? So it should be so it's a normal fault. All right. I mean, you wouldn't necessarily know that. You'd have to know something about the state of Nevada, all right, and know something about the fault lines in the state of Nevada. All right. So, yeah. Anyhow, all right. So earthquakes. So we get this idea of plate tectonics and where these boundaries are colliding. Of course, this part right here, surrounding, are you going around the Pacific Ocean from the Andes Mountains through the Rockies through the eastern side of Russia and then into Indonesia, down. Uh, this whole thing is, of course, called the very famous Ring of Fire, right? And so you see most of the big earthquakes in the world in somewhere along the Ring of Fire. Not all of them. I mean, see, that's the other thing that I want everybody to understand. These boundaries are, we do know them. We know where they are quite well, but you can still have earthquakes in other places, right? Because the Earth is really, really old, and so there are fault lines that are deep within the Earth that just suddenly might move somewhere where you never expected there to be a sudden earthquake, right? But it's just because these fault lines are somewhere deep in the Earth, and there's just a sudden movement that takes place. All right, let's see. So this one, earthquakes. An earthquake can occur between the plate boundaries. Strain begins at depths as elastic deformation. So it tries to, it's just like a rubber band, right? You start to stretch the rubber band, that builds up stress in the rock, and then eventually it reaches the elastic limit, and the rock breaks, and that's how you get a fault. All right, so that's an important idea. So let's talk about earthquake measurement. So there was this guy named Richter who actually worked in California, um, and he developed this scale, and we still use the scale today, although it has slightly different meaning than it originally did with during the time of Richter. But it is a logarithmic scale, so each time that if you go from like a magnitude 1 to a magnitude 2, the amplitude of the the wave, if you will. We're really talking about earthquakes, but it's still the amplitude of a wave increases by 10, by a factor of 10. So, all right. So, and then the energy, when you go from one unit to another on the Richter scale, the energy increases 30 times. So, for example, if you go from a 1 to a 2, as I mentioned before, the on the Richter scale, the amplitude goes up by 10. If you go from a 1 to a 3, the amplitude goes up. Remember, each time it increases by a factor of 10. So 10, and 10 to the second power. If you go from a 1 to a 3, it would be 100, right? So that's the way that works. All right, there's a good picture of this. I'll show you that in just a second. And then, of course, we have. Well, actually, let me show you that right now while I'm still thinking of it, because I don't want to forget it. All right, so this is what I was mentioning. So off to the left hand side, we have the traditional Richter scale. So he originally set it to 1 through 10, and so for example, if you're below a magnitude 3, I mean, we can detect that nowadays, and you could even detect it during the time of Richter, who lived like 100 years ago. But humans don't really feel anything below a magnitude 3, right? So you don't really even notice it. Between a 3 and a 4, like let's say a 3.5. If it's a magnitude 3.5, you start to feel it. If I lived in Southern California for a while I was in the Navy, and in San Diego, and you like a 3.5, you might you'd have like a glass would shake or something like that on a table or something like that, or if you had pictures on the wall, the pictures would rattle a little bit, which is fine. As long as pretty much in Southern California, as long as things aren't falling off the wall, it's not considered a big deal. When you get above a 4, then you start to get relatively light property damage. Relatively light. I mean, it depends on what breaks. And then if you're between a 5 and a 6, you get some serious damage. Above a 6 is considered serious. That's a serious earthquake. Certainly above a 7 to an 8 is a major earthquake. And, you rarely see these type, an 8 to a 9, and even more rare, anywhere from a 9 to a 10. That's an extremely high, or extremely energetic earthquake. All right, so and these things. Unfortunately, there was one just relatively recently, in Turkey and part of Syria, and I think it was like a 7.8. And 20,000 people lost their lives. I mean, it can be unbelievably terrible, for the human population in these earthquake zones, and so it's something definitely to be aware of. And so this is the amount of energy. The energy increases 30 times with each step. All right, so these numbers are 30 times the amount that they were before. So that's just thinking about the energy. This is considering the amplitude. All right, let's go back to our slides. So we were talking. So tsunamis occur, of course, in the oceans. And these are different than like ocean waves. That like you might surf on an ocean wave or something like that. You don't want to surf on a tsunami. So tsunami is an enormous wave that just suddenly rises. There's very little warning that a tsunami is going to take place. They take place from a huge chunk of the earth that has moved, at the ocean basin. And because of that sudden movement, there's a huge wave. It has an incredible amplitude, and that spreads out through the ocean. And when it reaches the land, you have a huge, as it says here, a huge displacement of water, and that can cause incredible damage to the land and to people's property, and so forth. Okay, so tsunamis are, it can be extremely deadly. Of course, there was one with the earthquake in Japan. Right, I think it was 2011, if I remember correctly. I might be slightly wrong on that year, but that earthquake caused a huge tsunami, and that tsunami came to Japan and actually caused one of the nuclear reactors there, which was right near the coast. It was called Fukushima. The Fukushima power plant, it actually had a meltdown because the tsunami caused nuclear power plants need to have they have to be cooled off. They are cooled off through pumps and the pumps pump water, and because of the tsunami, the pump didn't have any electricity, and the power plant, the nuclear power plant, had a meltdown, and we're still dealing with the consequences of that meltdown. There's radioactive material that actually had entered the ocean. Very, very dangerous radioactive material. And anyhow, Japan is trying to clean it up. It was a big disaster. I mean, since then, actually, since that time, the cleanup efforts have continued. For a while, there was a huge area around the Fukushima plant, and it went out miles and miles from where the plant was, where people couldn't live anymore. I mean, if you happen to own property and your house happened to be in that radius around the plant, people couldn't live there for a while. And then, of course, Japan has been monitoring what the radioactive levels were, and I think people are starting to move back, because it's been more than 10 years now. But there are, if you were right where the nuclear power plant was, I mean, it's no longer in operation, or the one that the one that had the meltdown. I mean, there is radioactive material there that's going to be radioactive for thousands and thousands of years, and what Japan is trying to do is dispose of that in a good, clean way. I mean, if that's even possible. The biggest thing with the Fukushima plant was the radiation that went into the ocean, and Japan is, they're very dependent on the sea and sea life, and some of the radiation got into some of the fish, and so they're very concerned about that. All right, that's tsunamis. And that's the end of the chapter.